This is the video podcast for Chapter 22 of Field Methods in Hydrology, using hydrology in river restoration. Now, river restoration is just one subspecialty within the overarching topic of environmental restoration, but it's the part in which I have the most experience in and done a lot of work with, so it's the one I want to use to illustrate this topic for you. And also, you're going to see here in this video podcast that I'm going to be trying to integrate across all issues, not primarily field methods, but just historical analysis, understanding rivers, and of course, field methods will play an important role in the kinds of stream assessment leading towards different engineering designs for river restoration. So that provides a little bit of the context for this presentation. Well, the first thing is that in the view of many scientists around the world, the Earth is facing a great challenge in that ecological collapse is underway. So many people talk about the problem of global climatic change, but I would make the argument, and I know many of my scientific colleagues would agree, that it's not going to get us, or it's not going to be the primary challenge facing humans relative to the fact that ecological collapse is already well underway. Major species extirpations, dramatic changes in land cover, land use disturbing fundamental processes on planet Earth in almost irreversible ways. I mean, these are things that are happening that aren't just happening over the last 200 years as a result of human-induced climate change, but are comprehensive changes that have come hand in hand with the population increase over a few thousand years, and especially with modern industrialization. So there's a lot of problems that humans have caused for planet Earth, and restoration is something to be considered to try to deal with that. Unfortunately, we've reached a point as a society where we have such a high confidence in ourselves that it goes well beyond our actual abilities. That intent of society and desire to solve problems just, unfortunately, can't be matched by our technical and cultural prowess at this time. Meanwhile, science is progressing, and in some ways, science has fundamentally changed in that today, the rate of progress in terms of our ability to collect data and really try to understand the Earth far exceeds our ability to take that vast stream of information and process it, come to grips with it, and then turn it around into specific technologies and approaches for solving the world's problems. So science itself faces a crisis, even though it remains a very powerful tool for helping to solve the environmental problems that we face. When we look specifically at rivers, as I'm going to do in this video podcast, we have two major problems that drive the rest, which is first that 90% of the rivers, and I'll of course use the United States for example, but this is true worldwide, that most of the rivers in the world have been structurally altered. Levees, in-channel mining, damming, and so forth. Also, in the United States today, about 40% of the rivers do not meet Clean Water Act water quality standards for fishable and swimmable. So even though we've come off the precipice from the worst case scenarios, still we have vast amounts of chemical pollution. When you put those together, then you can imagine all kinds of biological responses that are highly negative as well. In terms of the physical alteration of the rivers, here's just an extreme example showing Los Angeles on the left and Brays Bayou on the right, two heavily urbanized areas where streams have been turned into concrete ditches. There may be some aesthetic appeal in this view of Brays Bayou on the right, but really in terms of the functions that would provide as a river, they're essentially non-existent. And so that's led to the idea of river restoration. So we'll have to look at what that means. But that includes things such as in the upper left, dam removal, and in the lower left, riffle enhancement or rehabilitation. In the upper right, gravel augmentation for lowland gravel bed rivers. And in the lower right, wood structures being used to help stabilize banks, especially in incised rivers. And you can also see these large boulders being put into the stream as energy dissipation structures, for example, or to focus flow away from sensitive banks. So what approaches should be used to understand rivers, and then how can that knowledge be used to promote suitable engineering to actually restore rivers, especially given that rivers span such a wide diversity of forms and processes? Well, we have to begin by looking at some basic definitions. So what is river restoration anyway? Strictly speaking, river restoration means to take a river that's been disturbed or degraded by a specific human action, undo that action, and alter the river back to the pre-action natural state. So this is, similar to art restoration. Like, you have some great piece of art, but it's gotten dirty. You want to like brush away all the goo and stuff, crud that's on there, and see the beautiful colors and patterns that were present in the original artwork. However, just like with art restoration, you'll find that many efforts to restore rivers lead to quite a few debacles where instead of actually restoring the underlying condition, an entirely new outcome results that isn't at all desirable or representative of the original state. So that's strictly speaking what river restoration means. It's a going back concept. Now, we often think of restoration not so much as a going back, but it's just like, hey, let's get this thing happy again or healthy or whatever the heck that would mean. So it's often meant in a far more general way than strictly meaning going back. And as a result of that, there is another concept or definition, river rehabilitation, which is also a going backwards idea, but it's one in which we're not going to go all the way back. We're going to try to improve it, get to an improved natural state, and it isn't going to necessarily be the pre-action condition, but it's going to be something better than what it is. Other things that might be going on, you could try to preserve natural river. Of course, people literally can move a river out of the way. So if like you're going to build a facility or a bridge or something else, like literally moving the river to a new location, but preserving its shape and function somehow. Cleaning up rivers, so getting rid of trash, of course, would be very useful, or chemical cleanups would be good, biological remediation. But there are other kinds of cleaning up that people thought they were doing to help rivers that turned out to hurt them, just kind of like with artistic restoration issues. And that would be the removal of wood, which was termed debris, and boulders, where in fact these were important habitat elements that are part of natural streams. Bank protection is oftenly cited as a river restoration action, but it's the exact opposite of it. Banks naturally collapse. However, there are times when rivers have become destabilized, and then you may have excessive or inappropriate bank failure, but that doesn't mean that bank stabilization is in and of itself a form of river restoration. It's just a defensive action that people have to take. So why do we do river restoration? And this would be true pretty much for any form of environmental restoration or environmental change. The first is that the person who wants to do it faces a concentrated benefit or burden as a result of it. So if they're gonna get some great benefit, then why not? So then they would want to go ahead and do it or advocate for having something done. Another reason is an unfunded mandate. So the government can pass a law, or the executive branch can declare an executive order or rule or interpretation that forces something to happen legally without actually providing any funds, just as this has to happen. We've also seen that governments can have money available for projects. Those can be directed by legislative branches, or it could just be part of normal allocations to those government agencies. And so then in their efforts, they may simply be tasked with finding restoration projects and funding them. And then lastly, there can be community activism. So you get groups of people of common interest together. They want to help the river, and they may do fundraising and institute their own actions to help the river. So when we look at river restoration or associated actions, then we have to consider to what extent can we rely on the science that we have, and what is the science that we have, versus, so in other words, is this an engineering problem, or do we still need fundamentally new science and therefore it's more of a scientific problem? And of course, it's a blend of those things. There are some things we know about rivers that are specifically geared towards river restoration, but there's a huge amount of holes in our understanding as well. So there's really two aspects that we have to think about for river restoration. There's an observe and assess phase, and then there's an intervention phase with a big question mark on it. The kinds of interventions that we can do are generally going to involve morphological changes, which means going in and changing, the shape of the river, like all the things covered in the stream assessment presentation of this class, like plan form, longitudinal profile, bed and bank material, cross sections, like altering the river itself, or we could adjust the inputs to the river, which could be flows or sediment supply regime or biological materials. Generally, to do that, you might need to make landscape scale changes like reforestation, or just getting out of the way, letting forests come back on their own, or maybe substantially more cutting, disturbance regimes, like whatever is going to affect watershed scale processes. But then also, if you have dams and regulated flows, adjusting the flow schedules for these facilities could be done as well. Now, how do you know when to do civil engineering and when to do flow adjustments? That's something that has to be done on the basis of observation and assessment. It's not a given that one is right and one is wrong. It may be that both are needed or not. And the key thing to understand is humans are just like ants. We've been all over the earth. We've been changing it in every way possible for whatever people thought they needed or wanted to do. So there's no one simple thing that can be done usually, but it's usually a cumulative set of changes that are driving what we see today. Now I'll give you a simple example. Let's say you have a road and they just paved the road right across a stream, just paved it, just bulldozed, paved. And now, the river, maybe it's in an arid setting anyway, so there's nothing, there's no flow sometimes. When there is, it just floods over the road. Or maybe they put in a culvert with a step in it or something like that. Basically something that is a barrier to flow, sediment, and of course prevents organisms from moving upstream or downstream. So in a simple case like that, river restoration could be as simple as just destroy the road, put the channel back to its original configuration where the road crossing was, both upstream and downstream, given any change that have taken place, and then put a bridge over it with no piers in the water, just a single span bridge, and get out of the way basically of the river. Of course, that's a lot more expensive, but it would solve the problem. So that's a case where you have a single action that you can identify. You can pretty easily characterize the pre and post project conditions. We understand the science of it. You just have to go and do it. Now let's take a bigger problem. Take any large river where you've had massive changes to the watershed upstream, logging, mining, road construction, urbanization, agriculture, all those complications, and plus all the changes in the river itself, leveeing, in-channel mining, damming, flow regulation. Put all these complications together and then say, okay, well, what do you do? And now it's dramatically harder, and we honestly don't have all the answers to that at this time. So the first part of river restoration has to be to assess the status of a river, and I think of it broadly in terms of ecology, because ecology is the interaction of organisms as well as how those organisms interact with the environment around them. So it really encompasses all aspects when taken in the broadest terms. So here we can look at physical, chemical, and biological things that are going on in the river. We need to know about the physical processes. These are the mechanisms by which water and sediment that are supplied from the watershed interact with the topography and vegetation to create the river pattern that we see and the processes that are there, including the fundamental disturbance regime that presents the environmental fitness criteria for the process of evolution. Well, chemical quality is going to be really important because humans do degrade that by putting all kinds of materials into rivers. So we have to worry about the abundance and transformations of nutrients like nitrate, phosphate, possibly even sulfate. Um, Natural organic matter could be really important. Inorganic metals, zinc, copper, lead, mercury, toxic organic compounds, all kinds of things that are used for, cleaning, degreasing, and things like that, or lubricants or insulators. These are all compounds, herbicides, pesticides as well. So these are all important aspects of the chemistry. And then in terms of biology, we think about it in terms of individuals, populations, and communities, and then worrying about what are the indicators of a healthy ecosystem in those aspects. But we also worry about the habitats, the physical settings in which organisms do different biological functions that they need to do, and then dynamics that are governed by disturbance regimes and how a system responds to change, which we could think of in terms of the resilience of the system. Have we broken the resilience of the system, and how do we get it back? Now, there's a lot here to cover, and I'm not going to use this video podcast to address either the biological or chemical aspects. It's just far beyond what this little presentation is aiming to do. But I do want to look at what we've covered this quarter in terms of the hydrology of the river and think about how that information relates to river restoration. So there should be a lot of synergy, and I can go relatively fast for this next section. A big part about deciding how to restore rivers relies on what we think we know about how rivers work. And a lot of that has come from going out and measuring rivers and studying what's in them, in all aspects. And in terms of the hydrology of the river, what hydrologists have done has been very fundamental to the basic ways in which practitioners approach river restoration today. So if we go out on the river and we measure them, can we get some basic guidelines for how to do river restoration? Of course, when we look at the hydrology of a river, we can think about how discharge translate into stage. And you may recall the idea of bankful discharge. We've covered that pretty heavily in this course. It's the flow that just fills the geometric shape of the channel and occurs about every once or twice per year in a temperate climate with a moderate grain size of silts and sands, things like that. The more extreme the grain size, the more dry the climate, then bankful discharge tends to occur far less frequently, and even when it does, it tends to be less important in the processes governing the river. So how do we get to the relationship between stage and discharge? Well, you may remember we had Manning's equation, and it tells us that the discharge in the river is related to the hydraulic radius, which is typically related to water depth. And so we can, collect data and fit Manning's equation to that and have that relationship. We can also look at what are called attestation empirical relationships, which tell us the whole range of how depth, width, and velocity in a channel change with discharge. And here's some examples from a river that shows that. And you can see that even with highly precise measurement, there's still a fair amount of noise. This is on log-log scale. And so while this explains some of the basic aspects of how discharge controls these things, it doesn't give me a lot of confidence that discharge is the only or even primary control of some of the key river processes that exist. And so, for example, here you could see, what is this? Velocity can range from 1.3 to almost 4 feet per second or something, so that's such a wide range. Now other discharges, there's much closer, but it still has a range. And when you're talking about engineering, the level of uncertainty of having even 30% error can be quite dramatic in engineering compared to what we would normally want to have when you build, say, a car, or a bridge, something like that. But these relationships do help to show that for a given discharge, we can size and shape a channel to carry that flow. We can also remember from your probability approaches to hydrology that we have a typical skewed distribution of flows, with large flows occurring relatively infrequently compared to low flows. And so this is the annual peak flow series. So that gives us a sense that how much work gets done will vary because a river that has really low flows a lot of the time, maybe it's not able to do much work, but it's doing it all the time. So over 50 years, that could result in some very important changes to a river. On the other hand, these very large floods that could do dramatic work may occur so infrequently that they're not so important. Or when they do occur, they could create such dramatic change that they could create a legacy that could last thousands of years on the landscape. We can look at sediment transport. Here is suspended sediment load as a function of discharge. This is that depth integrated sampler. We talked about that earlier in class. And you can see that when you use that, you can get a relationship between load and discharge. Again, we see wide variability here, indicating that just knowing this relationship really is inadequate for river restoration in and of itself. But it does show that it's important to consider flow as one among many variables that control suspended sediment load. Same thing for bed load discharge, so the stuff that's rolling and tumbling along the bottom of the river, which in fact is constituting change to the channel. And we can see that as discharge changes, it generally does go up, but the range of variation can be quite different. In this slide, the red dots are showing data from a Helly-Smith sampler, and the black dots are showing from a net frame trap. And I've talked about these earlier in this class. But you can see that, for a relatively small change in discharge, we can have dramatic changes in bed load transport with high uncertainty. So discharge isn't the only factor, but again, this is a commonly used relation that can help to guide river restoration, as I'll be showing you shortly. So if you put together these different concepts that bigger flows occur less frequently, and when they do, they move sediment, and the movement of sediment constitutes channel change in some cases, then what that means is that we can define the flow that moves the most sediment. Without getting into the math of this, you're basically just taking this frequency distribution of flow, this curve B. Okay, that's the one like I showed here. Okay, and you put that together with a function that governs sediment transport, which is shown here as A, and that would be from these past two slides. They would both fit this form. If you integrate these two functions, B and A, together, you get the function C, which tells us that for these small discharge events, the amount of work done is relatively little. So even though they occur very frequently, they're not doing much. At the other end of the spectrum, you have very large events, but they occur so infrequently that they're also not doing much. And so if you integrate, there's some balance where storms are doing enough runoff and enough work to get the most bang for the buck. Now, the actual shape of this curve and what discharge yields this effective flow has to be determined for every river on an individual case. It could shift towards the lower end, it could shift to the higher end. There's too many factors involved to say what that would normally be. But it's the idea of it that matters. And so some people think that that happens at bankful discharge. There are cases of channels where that would be the case, but I would say that it isn't necessarily the rule, and especially in semi-arid and arid climates, and especially with coarser bed material, that just isn't realistic. So, but it is something that is commonly used in the river restoration community. Here are some examples of some bankful discharge relationships that show that if we look at what is the width, depth, and velocity of a river when bankful discharge is occurring, then we can see that there are relationships that exist there that could help us to size a river empirically for those flows. So if you could say, okay, I want to design a river to say have 1,000 CFS, then I could size it with these depths, widths, and widths to get that. To get the velocity, of course, you can adjust slope or you can adjust bed roughness. There are some other basic empirical functions that exist that can be used in river restoration as well. So if you go out and you measure the size and shapes of different patterns of rivers and things, and you compare them, you can find, for example, that the length of a river meander is proportional to the channel width. It's about 11 times the channel width. And of course, when you look at this noise and it's a log plot or whatever this is, then the fact that this is 10.9 and 1.01 just makes me cringe, because it's another example of the abuse of significant digits in science. Would you really design a river to 1.01 given this? No. It's basically saying that there's a linear relationship here. Similarly here, meander length is related to the radius of curvature. So how tight is a meander bend, and basically saying that that equals 5 times the radius of curvature. Okay, so I've just blasted through a whole lot of empirical relationships between flows and patterns in rivers in terms of primarily cross sections and planform patterns. And this summarizes some of these. So we have the width, depth, and velocity associated with effective discharge, which could be taken to mean bankful, but I don't recommend it. We have relationships between suspended sediment load and discharge, suspended bed load and discharge. Lambda is meander wavelength as a function of width. Let's see. I have to think about this. Ln is meander length. I'm trying to remember what this lambda is, but it's just another wavelength or frequency or something. Okay, so then we can also look at the slope of a river, and it can also be defined. I didn't cover those examples, but here are many functions that govern the slope of the river. And then we can also look at the sinuosity of a river as a function of width and depth, which in turn can be as a function of effective discharge. So anyway, these are examples, and there are hundreds of journal articles that exist that show these kinds of functions that people use for river restoration design. So it raises the question, does this kind of empirical information translate into good design? Because hey, you've taken this course now and you can go out and measure all these yourself. I've taught you all the ways of doing it. You just need to practice and have some trial and error, and you can go for it. But where does this get you in terms of river restoration? The way this is implemented is called the reference reach design method. Just basically, it's a simple way. There are formal names of each person's pet name, but anyway, it's basically a reference reach approach. And what this means is you look at your river that you think is degraded, and then you go out and you try to find other rivers in your region that are not degraded, or at least have key functionality that you'd like to mimic. And this is essentially a mimicry approach. What you do then is you measure empirically the different aspects of the river according to the different relationships that I've just shown you. And then you take the line from those empirical relationships and you come up with an ideal or archetypal stream based on that for the size and shape you want to have, and then you can use that. And so as a result of that, if I go back one, people have gone around whole regions like the entire state of North Carolina or Maryland or Colorado. And within a particular region like the foothills, or what they would call these like a Piedmont region or the coastal plain, where there are generally similar conditions, people have measured all these things and come up with these empirical functions to then be applied as a systematic approach for any one particular river. Of course, if you look at these functions and say that I was restoring the river and it was right where this dot is, you're designing something to the line. So if there's some local factors that would drive it to actually have a longer length, that wouldn't be captured by this. But the idea here is you're using this data to get the central tendency, and you're assuming that discharge is not only the primary control, but it is the control, and that other things will matter so little that it won't affect the consequences of how that stream functions. So typically what you need to do is you need to get the bankful and effective flows for the site you'd like to restore. Once you have those values, you can put that into all these functions and get everything else. So how do you get those? Well, you could use field indicators. Remember the video on how do you find bankful discharge in streams. You can do a flood frequency analysis and assume either that bankful discharge is the 1.5-year return interval event, or using regional indicators of what the recurrence interval should be. You could substitute in that. You could estimate bankful discharge based on basin area, which there are empirical relations for that. And finally, you can calculate what that should be for different sediment transport relations that you want to have, which is far beyond what we're covering in this class. In fact, there's probably 20 different ways to get these things. Typically, people rely heavily on field indicators and flood frequency analysis, but there are many other ways to go about it. There are a lot of problems that this approach faces, and of course, because this has been used so widely, and it has in fact been adopted by law in some states, or at least by rule, if not by law, it's been standardized in such a way that it's really important to think about what the challenges are. And I'm not going to read through these, but I encourage you to pause here and just think about them yourself a little bit. Another important aspect is that it considers river restoration from just one perspective. That is to create a single threaded channel with a typical size, shape, and plan form for that setting. But it neglects all the other forms of diversity that occur at the finer scale, which could include how a system looks at low flow, what's happened to it during floods. There's all kinds of diversity that takes place in rivers. What do you do about wood and boulders, complicated riffles? What about when water is flowing perpendicular to the channel? There's all kinds of things that happen in natural settings that are appropriate things for rivers to do that almost become like a matter of gardening or just aesthetic design based on individual experience, and so that isn't very satisfying out of this approach. There's also a problem that comes up, which we could call the uncanny valley problem in river restoration. So for those of you who don't know, the uncanny valley is a concept that comes up in Hollywood and video games and in robotics. So if you look at this woman in this picture here, you can tell there's no doubt that is looks like a human being, right? But there's some things that are sort of subtly disturbing that could lend you to say that that's either not a real person, or if it's a real person, there seems like there'd be something wrong with them. And what this has to do with is the idea that if we look at this graph, when you try to make something in a human likeness, then the closer you get to human likeness, the ability of a human to perceive that as like a human actually goes down into this area that's called the uncanny valley. So if you start with an industrial robot, we know for sure that that's not familiar as a human at all. And as you get to something like towards this picture, you're getting more and more familiar. But eventually you reach a point where something looks so bizarre that it falls into the uncanny valley, and it's highly disturbing. What we see with river restoration today is that people are making rivers that in many ways resemble a river, and in fact can be, they can be aesthetically pleasing to someone who doesn't know what they're looking at. But when you know what you're looking for at a river, then there is a disturbing unease about them, in that they're missing a lot of important elements that fall into this uncanny valley that if it was quite different, you might not be able to notice that so well. So we have to ask the question, do rivers that look like rivers or even have flow variations like rivers, because that's another form of mimicry, Do they actually behave like rivers? And what does behave mean? It means processes. It means mechanisms. Going back to those slides I showed you about physical processes, chemical quality, and biological health, does it have all of those things going on, or are we deep in the uncanny valley? So let me give you some examples. These are going to be examples that we can classify as not yielding the processes that should be there and have been fairly controversial, in fact, in the real world. But they're ones in which practitioners would say basically aren't necessarily failures, but are just cases where the river decided to change through time from how they were when they were first built. The key here is, what is the foundation for design and what was the outcome relative to the foundational concepts? So there's a place on the East Coast along I-95 near Baltimore, Maryland called White Marsh Run. It's a rapidly urbanized community. There's IKEA and other things along here. And so a long time ago, the Corps of Engineers facilitated the entrenchment of this river to produce a satisfactory 100-year conveyance in the channel, and it basically resulted in the channel becoming disconnected from its floodplain on purpose so that then the floodplain could be urbanized. And you can see here the I-95 corridor and the interchange there in White Marsh Run. Also in the vicinity of it, there's an IKEA, at least this time, and there was a lot of development of commercial on the floodplain. So now from a reference reach perspective, this is a little stream not far from White Marsh Run called Haha Branch, and it's typical of the coastal plain in that it's sandy substrate, there's bank vegetation that's falling in, relatively well connected to the floodplain. You can see it's meandering. Now let's take a look to see what they did when they rebuilt White Marsh Run. When you look at those two photos, they're remarkably similar. Look at the size of the streams, and granted I don't have a lot of size indicators, but the shape, it's just stunning. Except you can see some of the indicators of why we're deep in the uncanny valley. Haha Branch is all natural substrate. It's a forested floodplain that's well connected, and there's no problem with that. It has steep cut banks that are cutting. It has point bars that are growing. When we look at White Marsh Run, you can see that there's riprap at every single cut bank. It's because this river was not intended to be allowed to do what natural rivers do, a process of meander migration. And that's not the only issue here. So they did what are called bioengineered bank stabilization, which is a combination of boulders and root wads that are intended to stabilize the banks and promote vegetative growth. Now the idea here is when you do construction, you need to, you're dramatically altering the channel and you're making it highly susceptible to erosion. So putting in some stabilization and promoting quick vegetation growth in the first few years seems like a good idea. On the other hand, once that vegetation is grown, this other stabilization is not removed. It doesn't go away. So this is a permanent stabilization intended to destroy the basic processes of how rivers work for a good reason. Because when you got IKEA next door, and I'm not trying to pick on IKEA, but when you got commercial development next door, you're not going to let the river wipe that out. Here you can see how steep the bank is. So in a way, the river is incised, and as a result of that, the river, it doesn't have the width of floodplain it needs so that when it flows over bank, the energy is dissipated. And so as a result of that, they set the banks back some, but then they just rip-rap the heck out of this thing, which again precludes natural meander migration taking place. And this is a violation of climatic principles in general because this willow post is something that works well in a little bit more arid climate like Colorado, where you may actually have a few years to get that stabilization, but it just fails in a state like Maryland with a temperate climate with high flows every year that it's just not going to hold up. Another thing that we saw is systematic meander bend cutoff throughout the whole river corridor. The reason for that is because the meanders, of course, there's no function in geomorphology that tells us what these should be. Should it be a sine function? Should it be a sinoidal function? Should it be some sort of noise function like Perlin or noise or who knows what? What should the shape of a meander look like, you know? And so they just made them generally sinusoidal for lack of anything else. But the river's like, nah, I don't like that. I'm just going to cut all that off and go my own way, in general going straight. Now, let's not mistake this for a river choosing to do what it wants to do and therefore creating the correct shape. We have a degraded river that's been changed to a new degraded form, and the river is behaving in a new degraded way. You could call it a natural response, but it doesn't mean it leads to a natural outcome. So the solution that they did here was that they just came in and rip-wrapped every single meander bend to prevent that from happening. When you force a channel into a shape, it's no longer a river channel, it's what I would call a flume. And this is a very characteristic aspect of the uncanny valley in river restoration. When I look at these types of projects, I can really feel that flume aspect to how they work. It's just like if I go to a resort town somewhere and they have a concrete flume that you can go swim around in. When you get in these rivers and swim in them, they feel just like that. They're really uncanny. Then when we look at these functions that are being used to design these restoration projects, we find that they're just not accurate enough. In fact, if you look at the distribution of error around the line, you'd find, like, for example, with width, for this is a classic data set from one of my mentors, Lucian Brush, from 1961. It wasn't ever designed for river restoration use, but if it was used for that, for the rivers in Pennsylvania where it was developed from, you could see that 40% of the rivers would have the wrong width by 10 to 30%, and about half of them, or 44% of the time, the error would be more than 30%. So that's pretty significant error for width. When we talk about processes in rivers, there are many processes that are there. I just want to pick on one because it's really important in geomorphology, because rivers don't just exist as flumes. They actually have bed features like riffles and pools, what I call morphological units. You can think of not just riffle and pool, but runs, glides, slack waters, recirculations, backwaters, as well as and you get up a little higher on the banks, lateral bars, medial bars or islands, and point bars. So there is a process that's been talked about called velocity reversal that is actually used in the design of these reference reaches. But it turns out that the mechanism that's built into those designs is wrong, and we have a much better understanding today of what the real mechanism is. And I guess I have to decide how much I want to go into this. But the idea in general is that at low flow, riffles look fast, right? Because they have, if this is a longitudinal section down a river, so you go from riffle, pool, and this is the water surface elevation there. And so riffles are fast and pools are really stagnant looking. At high flow, it turns out that a river tends to take on the slope more like the valley slope than the local slope of the riffle pool sequence. Now, if you use very simple mathematics, and I've been through this math earlier in the quarter, and I've derived these equations for you, as you'll recall, it tells you that the shear stress in steady uniform channels should be proportional to the hydraulic radius slope product. And in this case, for hydraulic radius, it's usually similar to the depth. So it's like the depth slope product. However, by definition, if the bed is undulating up, down, it is not a uniform channel. It's not even remotely close to uniform channel, so these are the wrong mathematics. But this is the mathematics and concepts that are embedded in key reference reach approaches. On the other hand, we should be thinking of riffles as nozzles. Flow is being constricted in there, it creates a backwater behind it, and then a powerful jet that hammers through there at low flow. Well, it turns out that the vertical constriction that happens at a riffle, and you can see that in this thing, like the depth above the riffle is small and the depth above the pool is high. That's a constriction expansion scenario. Well, it turns out, and you can see it in this topography in the bottom map, look, this is a top view, riffles tend to be wide and pools tend to be narrow. And as a result of that, what happens is that at high flow, riffles are not so constricted by that bump in the bed. They actually expand because their width grows faster than the width of the pool. So actually the cross-sectional area in a riffle is higher than the cross-sectional area in a pool during a flood. And as a result of that, the nozzle changes from the riffle location to the pool location. I know this is a difficult concept. It isn't like at the heart of what this class is about. But the point here is that rivers are being designed on the basis of one concept based on an early understanding of rivers that's been well supplanted by a new concept, and yet practitioners haven't changed in light of the new concept. This is illustrated in two examples. One is in a place called Bear Creek, California, and another one I'll show you is in the Central Valley of California. So here is a wet mountain meadow, and you can see the green in the middle. That's where the channel, that's where the channel is located now. But originally, the channel was located where this red line is. It was incising into the channel. It had check dams. And so there was an approach to restoration called pond and plug. It means you dig ponds out on the floodplain, and then you use that sediment to plug up the channel enough to essentially erase it from the landscape. Then you may choose to either let the water spread out and create its own new way, reoccupy historic channels, or build channels explicitly using the reference for each approach. And that last approach is what was done here, kind of like where the blue line is. And that's where the green, the greener area is in this meadow. So here's an example where not only did they change the shape of the channel by building a new channel, but they also then lined that channel with gravel to also give it appropriate substrate for that system. And what happened is that everywhere there was a riffle, the sediment eroded away and then it deposited into a pool. Now look at this pool. This pool was excavated from the side with an excavator, most likely, and you can see that in this construction, the riffle has a very uniform shape that doesn't change with discharge, whereas the pool, not only is it super deep, but it's also very wide. What this means is that no matter what the discharge is, the peak velocities are always focused in the riffle, and the peak deposition is always occurring in the pool. Now, if you look at the equations here, this tells us that that the change in the location of erosion and deposition should be controlled by slope and depth. So as the riffle becomes deeper, the pool will always remain deeper, so that isn't going to change. But what happens is that the slope of the river is supposed to become so gentle over the riffle and high enough over the pool to create an opportunity for sediment to route through the pool and move on. But what you can see here is that the pool is so ginormous, nothing can get past this. It's not a pool, this is a pit. This is like a hole in the river from which there's no escape. Now let me show you another example. Here's a place where they transition the river from one type of channel to another type, and in the process it has a very wide riffle leading to a relatively narrow pool. And in this case, it's so wide that now it's actually vegetating over. But at least it is stable and the pool is narrow, so it can remain scoured out. So there's a little bit of a problem here as well, because of course this is a semi-arid to arid climate where it's not just about a balance of water and sediment, but also vegetation. But in this case, it could be that the riffle is over-widened and is therefore too stable. So that's an important issue to worry about. Okay, let me show you another example. This is the Robinson Reach of the Merced River in the San Joaquin Valley of California. This is a case where they wanted to design the riffles to be fast enough to support anadromous Pacific salmon spawning, which means it has to have velocities of like 2 to 3 feet per second. But given the river, the only way they could do that was to constrict it. By decreasing the width for a given slope, then they were able to focus the flow and create higher velocities. And so what you can see here is that consistently the pools are wider. They're about 30% wider than the riffles. See how it necks down in each one of these straightaways where the riffles are? Also, notice that the meander here is relatively sinusoidal, which means it could have problems in terms of that kind of meandering that I mentioned before. And what you see here, in fact, is that in every single case, the gravel that was placed on the riffles is being pushed into the pool. And notice, if you can see that, okay, there's a little bit of vegetation growing there, but more importantly, there's something we call the effective width, which, as you can see, there's a giant eddy. I'm circling it right now. And the current in the pool is being funneled into a tiny fraction of the width. This is what the river is trying to do, is it's trying to fill in the pool. It's like looking at this huge pool and say, I want to fill this in. I want the pool to be about, maybe 1/3 the size that it is now, and I want it to be dramatically smaller than the riffle. If it's supplied with enough sediment, it will institute that change. So the problem here is that you've got to provide the right velocities for spawning, but you can't do it by violating the geomorphic processes that are there. And so this shows the relationship between velocity on the y-axis and depth on the x-axis. If you have velocities that are so high for a given depth, then you're going to be transporting these sizes like D84. That's the size that 84% of the sediment is smaller than, or D50 is the median grain size. So if you look at pre and post restoration sizes, you need to have, you want the depths to be, well, for any given depth, you want the velocity to be below these thresholds and in the salmon spawning threshold, which is this gray bullseye here. So what this shows you is you can build riffles that have suitable depths and velocities for spawning, but don't yield sediment transport. In this case, that principle has all been violated because the wrong geomorphic processes and understanding was used in its design. And so in my view, yeah, okay, if the river has enough sediment, it's just going to redistribute itself, but it's still a project failure because of the design was not specified properly relative to good theory. So in summary, when you think about empirical geomorphology, we do have some problems. It's too focused on individual cross-sections, and therefore it's missing important dynamics that happen in the transition from cross-section to cross-section. Basically, you have to switch to a comprehensive view of a river and not rely on cross-sections. It's overly reliant on regional developed tools that are then transferred to other regions. So if you develop something in a semi-arid region and then you apply it in tropical temperate climate, that's probably a bad idea, or vice versa. The underlying principles of hydrodynamics tend to rely on steady and uniform assumptions of rivers, which are violated in most cases of rivers. Again, they're assuming rivers are like flumes, and therefore they're building flumes, but rivers don't function like flumes. So there's been a lot of backlash to the reference reach approach to restoration, and one of the important outcomes has been the idea that, especially in regulated rivers, we should be trying to institute environmental flows. So a regulated river is usually one that has a dam or multiple dams on it, or other ways of diverting and redirecting water for human activities. The idea of an environmental flow is to put back some of the water, but not necessarily just according to its natural occurrence given by rain, but to drive specific ecological functions or processes. So for example, this graph shows different hydrographs that have been made for spring runoff in the Trinity River of northwestern California. There are, 5 different regimes, one for each hydrological water year type. And the water year types are shown in the table in the upper right. So let's just focus on the biggest one, which is blue. In the biggest one, water is delayed, and then a very large spike is released up to 11,000 CFS. And you can see that above 2500 CFS, it says that this water is for fluvial and geomorphic objectives, and below that, habitat and temperature objectives. Um, so in theory, this 11,000 CFS is an environmental flow release intended to do geomorphic work in the river. Unfortunately, I've done a lot of studies in this river, and my outcome is that this 11,000 flow is a tiny drop in the bucket with minimal geomorphic significance in the river. Specifically, if you think about vegetation that's here in the semi-arid climate of the Trinity River, 11,000 CFS is totally inadequate to rip out that vegetation and reinstate a pioneer ecological setting, which is important for the geomorphology of the river. In fact, I've seen willow and cottonwood survive 100,000 CFS on other rivers. And in fact, on the Trinity River, historical floods were more than 100,000 CFS, and this so-called environmental flood is supposed to do geomorphic work at 1/10 of that with 11,000 CFS. So the idea of environmental flows is right, but just like with the empirical morphological approach, it's still based on mimicry. It's the idea of something that a process should be there without actually taking the steps to do the work to get it right. So that leads to this question, what is design anyway? I mean, is it just go out, look at the river, come up with some basic equations and build them into a design? And that's what I would call a prescriptive approach. Like there's only one way to do restoration and that's it. In fact, if we look at design and engineering, there isn't just one solution. And rivers are very open systems. There's many different ways to go about design. And they are all equally viable if you go through a mechanistic approach of figuring it out. And here's a quote you could read on your own, but it pretty much emphasizes that design is one part experimentation and one part calculation. So you do your best to figure things out, you try and experiment, you see what happens, and then you iteratively design until you get the outcome that you want. So there is a process of expanding to many alternative solutions and then determining what actually works best for all the constraints that you need. And that leads to the alternative to mimicking nature with either reference flows or reference morphology and switching to mechanisms or processes. You conceptualize the system, sure, but you can't stop there. You have to make specific tractable design hypotheses about how it works. You then have to do mechanistic tests. It could be laboratory experiments, could be computer models, and then analyze that and figure out whether that design hypothesis holds up or not. So for example, you could have a design objective like fish spawning habitat in a river should have geomorphically sustainable in a dynamic flow regime. And I didn't say that very well, but you can read that. So what's the hypothesis of this? Okay, well, the hypothesis is that scour of substrate out of pools and deposition onto riffles is needed to occur during floods, but we don't want that to occur during the low flow periods when it's being used as habitat by the fish. So we need to build rivers that have the right mechanism to do that. And it isn't the velocity reversal with the mechanism that was shown before, but it's something called flow convergence routing. And so that's another mechanism. So how are you going to test that? Well, you could make a design, you can run hydrodynamic models and see if that mechanism is there. And then you keep going until you get the design that yields that. And then even after you build it, you then see what happens during flood and find out, did in fact riffles grow and pools scour? To do this requires something that I call near census river science. It's the idea of treating a river as a complete population, looking at a spatially discrete census, essentially, of what is out on the river, and then bringing that data into very detailed models and experiments of how the river works. I mean, this just shows the wide range of things you can do. You can collect all kinds of data. You can do a variety of models, of which two-dimensional hydrodynamic modeling is one, and I teach a class about that. It's a whole bunch of GIS kind of work that goes into it, so that's all stuff that can be covered in other classes. And then ultimately, you're taking that predictive modeling and data to analyze alternative management and restoration scenarios. Let me show you an example of a predictive model. Here's a river in a floodplain, and here's a model that predicts or really simulates how it would be migrating through time. It's called the Meander Migration Landscape Evolution Model. Don't worry about the red blotches, that's a whole nother thing. But what you can see is that we have the ability to try to simulate behavior of rivers in many different ways. And we can use models like this to guide our understanding. A lot of times what happens in the rivers is governed by random processes. So it's hard to get the specific trajectory of the future figured out. But we can see what the tendencies of rivers would be. And that's where this kind of mechanistic predictive modeling really provides its strongest use in river restoration and management. So finally, what is our job as scientists as you head out into the workforce to work as a hydrologist or in restoration? I mean, you need to be part of the team and to be a team player. And what that means is that our job is to convey science and educate people about how the river works, but it's also to be helping to do the job of guiding people as best as we can on a team to see this as a hypothesis-driven scientific experiment. We want to show people that there are links between biology, physics, and chemistry, and help them figure out how we do experiments, that restoration is not a solved problem in science or engineering. So we need to take a scientific approach to do it. And then we also have to find fundamentally new ways to answer questions about how rivers behave so that we can better understand ecological functions and how to fix them. Also, it means that we have to think of science in a more hands-on political, social, economic context than just hiding off in academia and criticizing other people. We have to be involved and take a problem-oriented approach. So in conclusion, restoration is one part scientific discovery. I mean, hydrology has played a huge role in river restoration. But on the other hand, there is an engineering part of it too. We have to respect and honor that engineering has figured out a lot about how you design and build things. And so there's an interplay between science and engineering that works best when they go hand in hand. Just because engineers or scientists have made some mistakes and done some terrible things before, like everyone else in society, doesn't mean we should throw out all of their tools and abandon it and just wing it. Okay? We have to have robust techniques. And overall, we have to remain humble and recognize that we have a long way to go, but using the kinds of skills you've gained from this class, I hope you have the ability to go out in the future and tackle these problems as scientists and solve restoration problems for the benefit of society.